Okay, so let's review briefly what we learned last time. So we showed that the generating function for the moment of orthogonal polynomials can be written as a continued fractions like this. And then we showed that its kth convergent, which is a rational function, can be written in this way. Where is the exact statement? Yeah, we showed that the kth convergent can be is the generating function for all Marchkin path with bounded height, and yeah, if k approaches infinity, we get the usual weight. And today we will see some interesting connection with this and what's called a Bade approximant. So let me tell you what that is. So let px and qx be polynomials of degree p and q respectively, okay? And we say that p of x over q of x is a Bade approximant of type PQ, their degrees, for some function f of x. If we can express f of x as a formal power series, and if you divide this, if you subtract this rational function, then we get a formal power series whose lowest degree is at least p plus q plus 1. So something like that. So Bade approximant means that we approximate this using a rational function, and the approximation is good in the sense that the lowest term of the formal power series of Taylor expansion has degree greater than or equal to p plus q plus 1. Okay. So we all know very well about the Taylor expansion, and that is a good approximation of the polynomial of a function f. And the idea is we approximate a function using polynomial, namely Taylor polynomials. But here we approximate this using rational functions. But rational functions are better than polynomials in many ways because rational functions can deal with poles. When you have for instance, a rational function here, it has a pole at x equals 1. So we can talk about, we can somehow get a better approximation of this when there is a pole in this function. Then if you only use polynomials, you cannot really tell the property of pole of this polynomial because polynomials don't have any poles. So, but the fact is that if fx is a power series, then there is and if how can I say if okay, let's say with a Bade approximate of type of given type, then it is unique. The Bade approximate is unique. It's a fact. Okay. And our corollary here is that the one that we had here, this is a Bade approximant of the generating function for moments. That's the claim. So let me state the claim. So let f be the generating function for the all moments mu n, which we specified b's and lambdas. Then for integer k, non-negative integer k, this rational function that we considered before is using these inverted polynomials over pk plus 1 star. This is the unique, it is a unique Bade approximant. Of f of x of type, of course, k comma k plus 1. That means this is the best way you can approximate this using a rational function of degree, the numerator degree k, denominator degree k plus 1, and this is the best you can do. Okay, so proof is actually not that difficult because we know already quite well about all of this. So we know that this part here we know that this is equal to let me omit p and lambda because they're always there. We know this, okay? So
정의에서 그럼 시그마 밑에가 p 마이너스 q 플러스 1이어야 되지 않습니까?
네. 네, 그렇습니다.
플러스라고 말씀하시고
어디? p 플러스 q 플러스 1 저기 맞을걸요? 네. 질문이 어떤 게 질문이죠?
저기가 저렇게 되면은
네.
결과가 이상하게 나오지 않습니까? 지금
글쎄요. 한번 이따 보죠. 네, 일단 봅시다. 네. Okay. Let's see if the statement is correct. So here we need to show that this minus this has lowest term greater than or equal to 2k plus 1. Okay? Or 2k plus 2. Yeah, because this plus 1. So okay. Guys, maybe I can say r. Let's say r. Then f of x minus r of x, let's say, minus r of x is the generating function for all mu n minus mu n less than or equal to k. This. Is that right? But these two are of course not always the same, but they are the same if k n is big enough. So just let's see for what values of n this can be non-zero. So if mu n, so I suppose this is non-zero, or this is not equal to this. That means, but always this the set here, the generating function for all Marchkin path of length n, then generating function for all Marchkin path with bounded height. So this is always greater than or equal to this. So if this happens, then we have something that this is n, the height is k. We have to somehow go below this, and then we have to return to this. That means n must be greater than or equal to k plus 1 times 2. K plus 1 for this, and another k plus 1 for this. So it is greater than or equal to 2k plus 2, so k plus 1 plus 1. So it is greater than or equal to this. It's like this. So it does satisfy the definition of the Bade approximant. So that's the proof. Okay. All right. And we're gonna now move on to the next section. But the next section, what we want to do is to find the refinement of this result. Let's see the statement. Here, we found the generating function expression for the generating function for all Matchkin path, starting from 0 height and ending at 0 height with bounded height k. We want to generalize this so that we can start from any height and end at any given height. Okay, so that's what we want to do. So let's look at the next section. Matchkin path with a fixed starting and ending height. So we define this much NRS to be the generating function for all Matchkin path, starting with starting point 0, R, ending point n, S. So it's like the length is n, but the starting height R, ending height S, like that. And also we define and and of course we also have to define much and rs less than k is the all set of all pi with height, maximum height less than or equal to k. So in other words, it's bounded by k over here. And we're gonna define mu sub nrs less than k, generating function for all Matchkin path in this set. Weight pi with weight given by these two sequences b and lambda. Okay. Then the statement is the following. I'm going to state the theorem. So suppose that we have integers rs less than or equal to k, and there are two cases. If r is less than or equal to s, then the generating function for this mu and rs x to the k. Okay, let me put it this way. X s minus r. This looks somewhat complicated. Let me omit b and lambda, okay, just to make it easy to write. Over pk plus 1 star x if r less than or equal to s. So, and lambda s plus 1 dot 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 lambda r, and the same thing with r and s, switch it. If r greater than s. Okay, there are two cases, slightly different. These are pretty much the same, but we have some different factors there. So yeah, this is our goal in this section is to prove this refined result. So you see, if both r and s are equal to 0, then this is the usual one, and this they all disappear, and we have only one delta. This is exactly the thing that we saw before, so it's a generalization. So there are several proofs first, we can give a combinatorial meaning to this. This is basically a generating function for Hubbard tilings. And because then we can move this to the other side, and then we have a pair Hubbard tiling, Marchkin path, and then we get another pair of Hubbard tiling, two Hubbard tilings. So we can find the sign reversing involution here with fixed points giving this quantity. That's one possibility. And this is something that similar to what we already did. And I'm not going to do this here, but we're going to see another proof. Well, actually, we will give two proofs of this. But first, we need some definitions. We need to set up something. So let's say V is a directed graph. And then we're going to assume that this is the set of integers. The vertex set is the set of integers 1 through m. And yeah, W is an edge weight. K is just some commutative ring. So think of this as a quantity attached to every weight, every edge. So it's an edge-weighted graph now. And okay. And let's say A is the adjacency matrix of the weighted graph G. That means the ij entry is the weight of the edge from I to j. Okay. This is a usual convention. It's a quite common situation. Okay. But just to make it concrete, let me give you an example, like 1, 2, 3, 4. Any m equals 4. Let's say we have a directed graph, something like that. Maybe some loop. Then I'm going to give weight here, like, I don't know, A, let's say A, B, C, D, like that. Then what is the adjacency matrix? So it's like 1, 2, 3, 4, 1, 2, 3, 4. So edge from 1 to 2 corresponds to the entry 1, 2. So here we have A. And this corresponds to 2, 3, 2, 3B, and 3, C is, 3, 2 is C, and 4, 4 is D. And the other entries will be filled with zeros just. If there is no edge, we assume that the weight is 0. Okay. So this is an example of an adjacency matrix. All right, and some definitions. A path of length n from U to V is a sequence of vertices where we start from index 0 and then end at index n. That's the length, such that first of all, the first element must be U, the last element must be V, and each U I minus 1, let me write it this way, is an edge for every I. Okay? Just like, this. So for instance, this is a path. Or we can go something like that. And this is also a path. And this, if you loop around several times, is also a path. And the weight, I'm going to define the weight to be the product of all edge weight. or this can be written using the adjacency matrix. You can also write it this way. These are all integers, so I define the vertex set in this way so that we can write it in a simple way. All right, now one more definition. P sub n u to v is the set of all paths of length n from u to v. And what is this? If I don't specify this means the union of all this. So the path, all possible path of any length from u to v. Okay, now I'm gonna state a lemma, two lemmas actually. So first lemma. So let I and j be the vertices in our graph, and n is non-negative integers. Then the generating function for all paths of length n from I to j with this weight system. This is nothing but the entry of the adjacency matrix raised to nth power, and it's ij entry. And actually, this is a pretty simple lemma, and then you also learn this in any undergraduate discrete math course or combinatorics course. And the proof is really immediate, I would say, from the definition of an, the multiplication. What does multiplication of two matrices mean? You know, this means generating function for sum over all, I don't know. Yeah, this kind of proof is proof that becomes more difficult if you explain it. So I'm not going to explain it. Think about it. This is easy. The way you multiply two, for instance, ij, you multiply this. This means you take a path from here to here, and then if you multiply again, then you have to select somewhere. Then it's like constructing a path. So that's it. All right, but this is the important proposition. Suppose that I minus a is invertible. Then the generating function now is the generating function for all possible paths from I to j, any length. And this is equal to the entry of I minus a inverse ij. And also this is equal to -1 to I plus j, I minus a. This is the inverse minor formula. Determinant of I minus a. Actually, this is what we want to show. This equality between these is just a minor inverse formula, so we already know that. So we only need to prove this. But the proof is quite simple because what does this mean? You basically consider all possible length n, and then you look at path of length n, like this, right? But we know from this lemma, this is equal to generating function for all n, a n I j. Okay. So we have bunch of infinitely many matrices, and then we look at the ij entry and you add them all. But that means you add the matrices first, and then you can extract the ij coefficient later. That's the same thing. But if you look at this, this is the geometric series also works in this case. So this is I minus A inverse, the geometric series of this. If this is invertible, then this becomes this. And that's it. That's the proof. See? So it's really nothing but this simple matrix manipulation. Okay, now it's time to think about the generating function here. Now we need to look at this. But, okay, let me move on to the next section. So let's look at this. But if you want to use this kind of proposition, we need a graph and we need a path. But Machkin path can be understood as just a path like this in a finite graph, or if k is fixed. So in order to understand this, we're going to define a graph. Gk, g sub k, is the graph where v is the set of integers from 0 to k, and e is, okay, let me just, I think it's easier if I just draw the diagram. So 0, 1, 2, dot, 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 k. And the edges are like all loops are possible. And you can go any adjacent integers like this. And then we need to define the weight. And the weights are like b0, b. Loops have weight b's. And if you go up like this, it's like an up step. So it's the weight all 1. But if you go backward, the weight is going to be lambda 1, lambda 2, etc. Let's define the gk in this way. Then Machkin path is really with bounded height k, and rs is really a path in this graph of length n from r to s. Why is that? Because just let me give you just an example. 1, 2, 3, 4, 5. Maybe 1, 2, 1, 2, 3. So let's say r equals 2, s equals 3. So you go horizontal, down, up, up. Let's say horizontal. Then this corresponds to the path. The idea is you just keep you only keep the height. So start from r equals 2. So this corresponds to, now let me just draw the diagram in this way. I'm gonna rotate this in this way. Then this step, the path now corresponds to this. Start from here, and then you go to the same step, same point, and then you go down, and then up, and then you end over there. So it's really, a Machkin path is really a path in this. Because of this height bound, and then it cannot go below, it must stay in this graph. It cannot leave this graph. So Machkin path is really a simple object in this way. The Machkin path is a path in a line graph like this. It's a simple path graph like this. All right. And now that we have this graph, this is equal to, maybe I can just move this somewhere here. Okay, sorry. I'm gonna put x for everywhere, just to make sure that. Oh, this was a typo. Sorry. This must be n. You know, this means that we have to multiply x to every step, because this is the number of steps. So instead of having this weight, which will give us exact weight of the Mochkin path, I'm gonna modify the weight and then multiply x everywhere, so that it has the same weight as, but here, x, 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 like this. Then this is really the generating function for all paths of length n from R to S, weight of P. Yeah, I define the weight with x here so that I don't have to multiply x to the, I don't know, the length of P, just to make it simpler, make it look simple, but it's really the same thing. All right, now we express this as a generating function for all paths. Now we can use this theorem, this proposition. Okay? Maybe I can just copy this. Let me rewrite this. We have the different index by a proposition. This can be rewritten. This is now minus 1 to R plus S, the I minus A. Oh, by the way, yeah, because I define the weight in this way, what is the adjacency matrix of this diagram? Diagonal entries have x. If you go up, diagonal entries have b0, x, b1, x, like that, bkx. And then if you go up, that means here is the super diagonal, so x everywhere above. And then the going down means the diagonal is below the main diagonal, so is lambda 1 x dot 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 lambda k x. Okay? So, right. So I'm using this matrix. This, the R complement divided by determinant of I minus A. So, because we defined the matrix in this way, what is I minus A? Let me write this the more recognizable way. So 1 minus B0x, 1 minus B1x, and 1 minus bkx for the diagonal entries. And then the ones above the diagonals are like all minus x's. And the one below the main diagonals, they all have minus lambda 1x, lambda 2x, etc. Here minus lambda kx. So it's a tridiagonal matrix, all right? So we need to compute both the numerator and the denominator for this matrix, okay? All right, I think I'm gonna need this. Let me move this to the next slides. Maybe I can just copy them all. Just for reference, so that we can look at them together. Okay, so first, the denominator, lemma. The denominator, the determinant of I minus A is nothing but the pk plus 1 star of x. Why? Proof. Because they have exact same recurrence and same initial conditions, right? So let qk plus 1x be the determinant of this. All right? But then we can expand the determinant along the last row or last column. Then we get this recurrence. Qk plus 1x equals. If you expand along this, then you have the same matrix with one smaller size. So, but the entry is 1 minus bkx, qkx. But if you choose this or this, then you cannot choose anything there. So you really have to choose this. So you choose these two, then you get a matrix of size decreased by 2. So that is minus minus, but we have to multiply the sign for the choice of this. So it's minus lambda k x squared q k minus 1x. But this is exactly the same recurrence that P star has. Same P star. And same initial condition. Namely, Q0 is 1 minus B0. Oh, sorry. The index is K plus 1. So Q0 is, we have nothing. So it's determinant of MP matrix is defined to be 1. So Q1 equals, we have now only one entry like this. They have the same initial condition, so they must be the same. Okay? And now the denominator has been computed. So what about the numerator? The next lemma says that the numerator can also be computed. Equals, there are two cases, exactly the cases that we had in our theorem. I'm gonna even omit x. Oh, sorry. S plus 1 ps, k minus s star if r is less than or equal to s, lambda s plus 1 lambda r ps star delta r plus 1 pk minus r star if r is greater than s. Okay? Proof. It's really just considering this matrix with S row indexed by S and column R removed. This is like, so let's consider R is less than or equal to S this case. Then the matrix that we want to compute is this. So we have R here, S here. So it's R, S, R, S. We have to, this means we have to remove the row S. So we remove this, right? And then we remove column R. We are left with things right there. But see, this is a tridiagonal matrix. So this part, they are all 0. So we only need to look at parts that are here. So we have to look at this. Let's say this is B1. And also this, B2. And this, B3. Okay? But what is so what I'm saying is, left-hand side that we want to compute is the product of the determinant of three matrices. B1, B2, B3. But what is the determinant of B1? This is exactly the same matrix, only the smaller size. So that's PR star. This is PR star. And what about this? Exact same matrix with smaller size, but we have shifted all the indices by s plus 1. So it's delta s plus 1, this k minus, p k minus s star. What about this? If you look at this is not exactly aligned with the diagonal here. So it shifted a little above, or just one step above. So this is now a diagonal matrix. Lower triangular matrix, right? And the diagonal entries are exactly those over here. So this is like let's see, x to the s minus r with sign, I think, minus 1 to, of course, s minus r, but that will cancel with this. And because we are looking at this matrix of determinant of this, okay? So that proves this. Is that right? The same way, if r is less than, greater than s, we have exact same situation, except, instead of this and this, we have to remove, we have to change r and s. There are s and r, s and r. So we remove this and this. So B1, B3, they are in the same position, but B2 is now over here. And now this is a diagonal entry, and it's the upper triangular. And the diagonal entries are those over here. That means determinant of B2 is now minus 1 to s minus r times like lambda s plus 1 lambda r. Exactly, that's over here. So that's the proof, basically. So we have everything. We wanted to compute this, and then this is equal to the ratio of this. When we saw from this lemma that this is pk star, pk plus 1 star, this is this. That's exactly what's written in the theorem, and that's the proof. Yeah, so this is one way to prove the theorem. And I'm going to give you a more interesting proof, combinatorial flavor. So I'm going to give you another proof. So a combinatorial proof. Instead of using linear algebra, we can prove this directly using combinatorics. Using disjoint path and cycles. Let me tell you what they are. So we need to define something. As before, let G be a graph, directed graph. V is the set of integers 1 through m, and we have an edge weight as before. That's the same situation. And we define what a path is, and A is adjacency is the adjacency matrix of G. Okay. Now we define the path, so we need to define a cycle. A cycle is a path. Let's say from 0 to n, such that the first element is equal to the last element. And when you say a cycle, we will always identify a cycle with its cyclic shift. We will identify, let's say P with it's a cyclic shift, meaning P should be identified. It should be considered to be the same thing as Uj, Un, U0, and Uj. I shift them like this. So in other words, if this is a cycle and this cycle must be considered to be the exact same thing, we're gonna treat them equally. Okay. Now, and we say that now a path P, let's say U0, Un is self-avoiding. That means doesn't have any self-intersections. If Ui, Uj are all distinct for all Ij, except possibly that this may happen, may or may not happen. If it's a cycle, this is true, but if it's not a cycle, it's not true. But this is allowed if it's a cycle. Okay, that's what I mean. So this is self-avoiding, but this is not self-avoiding. Yeah, the intersection. Okay. We need some more definition. Yeah, and we have a collection of path, PT, let's say. Collection of path is disjoint if first every PI is self-avoiding. They don't have intersections by themselves. And second, we have no intersection between PI, PJ. They don't intersect at all. That's what a collection of path is disjoint. But notice that this is a collection, not a sequence, so we don't really worry about their position, their order. So we only look at them as a set. So for instance, this is or maybe we have a path as well. This collection is a disjoint collection of paths. Okay. Cycles are also paths, so yeah, this is good. All right. Now we're gonna define two notation. Gamma is the generating function for all collections. Let's say C, script C minus 1 to T, weight of all. We know what the weight of a cycle means. It's a product of all the weights in that cycle, the edges in that cycle. And where C, this C is the set of all collections of disjoint cycles in our graph G. Okay? Just imagine that. So you think of all possible ways to collect cycles. You may select nothing, so the empty collection is also a possibility. Or you can select only one cycle, or only this, or 2 or 3, etc. As long as they don't intersect at all, like this joint, then it's in the collection. And finally, gamma I comma j is the generating function for all. Now it's a pair, so a path and a collection. So which I gonna write script Cij, where we multiply all the weights, including the path. The first one, so it's a pair. This is a path. This is a collection of disjoint collection of disjoint cycles. So it's -1 to t, the same thing like this. Where of course this means that this is a path. This is in C, and maybe I can say more than that. And such that P and C1, including P, they are all disjoint. Let me give you an example. So instead of giving you just a precise or concrete example, I'm going to give you just a rough idea. So gamma has elements like this, or maybe 1, 2, 3, 4, 5, something like that. You have some cycles, and you have some missing elements. That's fine, because you don't have to select all the vertices. So this is an element here as a set. I mean, this is not there. These 3, if you collect these 3, there's an element there. And what about element of, say, 2 to 3? So 1, 2, 3, 4, 5, 6. Then you can go something like this and this. This is our path P. And the cycle can be like that. Maybe something. And maybe we have one more element, 7. So this, the typical element of this looks like this. We have path, the path must be there always, and a bunch of cycles disjoint, including the path. So no intersections at all in this configuration. All right, now we have all the setup. Then here comes the proposition. This is the generating function that we considered before, the generating function for all paths from I to j, weight of p. So, for instance, here if I equals 2, j equals 3, you consider all possible ways to go from this to this. You can go there could be self-intersections and many times as you want, and there's absolutely no restrictions here. But the interesting thing is, this is the ratio of this. So this can be written as generating function for all configurations like this, disjoint configuration with one specific path from I to j and some bunch of disjoint cycles divided by configuration like this, like the disjoint cycles. Okay, how can you prove this? Okay. But let me postpone the proof a little bit, because the proof is not difficult, first of all, but the application is more interesting. So I'm going to give you an application of this proposition. Let's postpone the proof. Now we want to prove this theorem. Where is it? Yeah, this is the theorem that we want to prove. We want to prove. Okay. So we need a setup. We define GK as before. So this GK is like 0, 1, 2, K. And then the graph is, maybe I can just copy the whole graph. Okay. We know that this is equal to, we know that this part is equal to this. That we already know, right? So we know that this is equal to this, and of course, by this proposition, that is equal to this as RS. R comma S over. Now, what is this? Let's look at this. What this is? What is this? You look at all possible disjoint cycles in this diagram, in this graph. But every cycle here, if it's self-avoiding, must be a single cycle of length 1 like this, or length 2 like this. You cannot go like any further other than just return to itself. Because, for instance, if you go, it will be self-avoiding. It will have self-intersection. And if you use a loop, you cannot use anything else. So you have only single cycle or a cycle of length 1 or this. That means, okay. But this looks somewhat familiar. We have to choose singleton or edge like this. Edge means like cycle of length 2. You either select this, or you make this, you don't choose this and then choose this. But this is exactly Favart tiling, right? So what I said is this has only cycles of length 1 or 2. So any element here, any collection, say C1 CT collection in this gamma can be identified with Favart tiling T. I'm going to give you an example. So, example. It should be clear if you look at this example. 0, 1, 2, 3, 4, 5, 6, 7, 8. So everything must be of length 2 or length 1. So this is an example in our collection, disjoint collection. But what is the weight? This has weight. The weight is always this with minus for every cycle. So this gives us x and lambda x and minus, so it's going to be minus lambda 1 x squared. And this has weight b0, b3x, but minus, so it's like that. And this has weight minus b4x. This has weight minus lambda 8 x squared. But this can be identified with this Favard tiling. 0, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7, 8, where 2 cycle corresponds to a domino, and single cycle of length 1 corresponds to a black monomino, like this. And these are red monomino. Missing points correspond to red monomino. And here we have to multiply. This has weight this has weight 1, this has weight minus b, 3x, etc. This is exactly, under this correspondence, what this shows is that this is equal to p k plus 1 star x. Because the weight here is different from the weight that we saw for the Favard tiling giving us the orthogonal polynomials. But we have inverted polynomials, so we have to have weight like this. That exactly corresponds to the inverted polynomial. Okay? So that means this is equal to this. This part is done. So the denominator is exactly like we wished. Now we need to look at this. But what is this? But what is this? And maybe I can give you an example. Okay, so 0, r minus 1, r s, s plus 1, k. Let's imagine that r is greater than or equal to s, so that we have arrangements of r and s like this. We have to go, so here we must have a path from r to s, but it's self-avoiding. So there's only one way to go from r to s, only one direction like this. And now you may choose some disjoint cycles, but they must also be disjoint with this path. That means we have to select disjoint cycles only from this part or this part. But choosing disjoint cycles here is exactly just gamma, except we have decreased the length. So this part is exactly p r star. Choosing disjoint cycles from this part gives us p r star. And here is the same thing, except the indices of the lambda and b labels are shifted by s plus 1. So here, this part gives us delta k s plus 1 p k minus s star. Because we have to select some, we may select some disjoint cycles there. But what is the weight of this? If you go this way, the weight is always x. Every step has weight x. So this gives us x to the s minus r. But what about the other way, the other case? I think I made a mistake here. R less than s, r greater than s. We have exact same situation. 0, s minus 1, s, r plus 1, k. But we have to go backward because we have to go from r to s. This is the only way. This gives us the weight. If you go backward, the weight is lambda. Wait. Okay, let me just write it down. S plus 1 lambda r. Why is this off by this? Okay, I think. Yeah, right. Yeah, I think I should have defined the weight x squared and lambda here instead of putting x and lambda there. Yeah, there might be some mistake in this diagram, but we want this instead of x attach it. And then here, this part giving us PS, this part giving us exactly what we wanted. And combining this result, we get the second proof of that theorem. Okay. Yeah, I might have made a mistake here, but I will fix this in the lecture notes. Okay. And in fact, these two proofs, I presented you two proofs, one using linear algebra, the other using more combinatorial flavor, but they are in some sense equivalent because this part and this part are exactly, can also be seen as the determinant of this and the determinant of this. So I will explain that later in the next lecture, the video lecture. Yeah, I think that's. Yeah, I also didn't give you the proof of this, but they will also be given in the next lecture. And yeah, that's it for today. I'll stop here.